with it. Okay, sure. Yeah, our great pleasure to host Professor David Atienza from EPFL to with the Duke, and also give this Athena Distinguished Seminar. Just give a short introduction about David.
Sure.
David is a professor from the EPFL. I'm not sure you should change your title now, I think, from today. But anyway, so the title saying, he's head of the Embedded System Library and the scientific director of the EcoCloud Sustainable Computing Center. I think that you offload this student to Nani, and then you became the vice provost. So his research includes a system-level design methodology for the multiprocessor system on chip (CPS) and also energy efficient computing server. He is also doing like a 2D, 2.5D and 3D power thermal aware design, as well as edge AI system, software hardware co-design for AI. That's why he had a lot of collaboration with us. He authored many papers, more than 450. I believe it's a number keep increasing, so I'm not sure it's the latest one. But anyway, so I have 14 patents, also including the ICK 10-year retrospective, mostly for influential paper awards. The DAG under 40 inventors, and also both CEDA and the CDA really career awards. Okay, better than me.
No,
I only received one.
I don't think so.
So. Okay, so I'm joking. So he's a fellow of IEEE, ACM, and has been chair of European Design Automation Association. Just for information, it's the largest professional association in our society. And actually, a couple of our alumni received the best paper dissertation from the EDAA. So yeah, thank you so much. Even that was not from you, Hans. Yeah, so. And also the ICK, EIC, which is the best, I would say the best transaction in our society, and the ACM computing survey. So if you really have any good survey paper, that is a full forum you should publish, but it's very, very competitive. Okay, so I will stop here and give the stage to David. Yeah, thank you.
Thank you very much, Jiran.
Yeah.
Thank you very much, Rayasi, for all the details and logistics. Everything worked great. I'm very happy to be here today. So the talk today will be trying to fit on the scope. Also, the collaboration that we have with the Athena Center is about accelerator-centric design for HAI architectures. And in particular, one of the main areas that we target at EPFL is low-power wearable design systems. So in this case, one of the first things I would like to go through, we are going to design systems, and that's what we're going to do in the talk today, but we're going to try to a little bit understand what is different from these systems with respect to you will have in a regular embedded system design that you have today. So one of the main things is about what you need to monitor. So in general, what you need to monitor is you see about why wearables are important for healthcare, and you see in this figure a little bit the reasons for death worldwide, which require monitoring. The largest part of it is non-communicable diseases. Okay? So even true, we have just passed a very big shaking in the world, which is about COVID. In fact, still, even the COVID period, most of the diseases that were happening in the world were not because of COVID, even though it was a huge volume, but still were not the largest. In the end, the largest was still about non-communicable diseases, such as the way that we live our lives, how sedentary our lives is, and stuff like that. So what happened is that if you go deeper into that particular category, what you see is that the largest part of it is basically due to two main elements. The first one is cardiovascular diseases. So still is our cardiovascular system, the heart in general, and derivations of problems with the heart. The second one, which is a bit funny, the name is malignant neoplasm. I'm not sure if the audience knows about that, but this basically means cancers that are cancerous. So anything that is related to cancer is actually becoming a huge burden in our society. And there we need to really find the ways to monitor properly essentially how you will actually be dealing with it. And the third part is non-communicable diseases, where it says other NCDs. These are referring in general to brain disorders. Anything related to the brain or electroencephalogram related malformations or pathologies. So if we think about that, and we forget about the cancer for the time being, but if we take cardiovascular diseases, brain disorder, respiratory diseases, you cover roughly 90%, sorry, like 75% of the whole thing. Okay, so if you want to do that, then you say, okay, what are the reasons for that? Let's forget about cancer and liquid other factors, but the behavioral risk factors of the three main problems are related to tobacco, unhealthy diets, alcohol, and physical inactivity. So these are the main reasons. No matter what you say, there are plenty of things that actually monitor that. But to be able to monitor all these and the reasons with all this, the link with all these elements, every person is different. So you will not be able to take a single approach to actually handle all the problems and prevent all these problems. You will need to have a personalized monitoring for every person to see how these effects, how these elements affect, or how this combination of parameters actually affect everybody. And for that, you need to have long-term monitoring, typically of lifestyle habits. And that's why HAI wearables become a very key, really a key technology today in many of the companies that are dealing in this area. So now, if you want to do that, that's on one angle that is important. The second one, that's why HAI is becoming even more critical, is the idea of you could have sensors and send everything to the cloud and monitor in the cloud. But the problem is that this is not really privacy preserving. So it's actually very risky because everybody would like to have a little bit of control of what this data, the healthcare data is being used for, because it can be used to help you, but it can also be used to realize that you're actually a very high risk factor person and increase your health insurance by a factor of 3. So basically, it's a little bit of a chicken and egg problem. You have to make sure that you monitor the people and the person is really controlled. And to do that, because it's really multi-parametric, very often AI is becoming these days, and machine learning is becoming very important area where you can actually tune the system accordingly. Now, if we take the other side of the picture, we take, okay, we take these HAI technologies, you want to develop foundational models or very well-tuned models for the person. The point is that these models are becoming larger and larger. So you see, these are the latest trends. So you see the operations, giga operations per that are required for the different models to get the highest accuracy. These are in general models that are used in healthcare. You see that they're in the order of becoming systems that you have at least 152 layers, 155 layers, huge amount of parameters. So this requires a completely new approach. And the reason for that is because in the literature, you have these AI models, and they're creating these own efforts, but these are not at all coupled with the way that we design electronics. Okay? So we need to really find ways to combine the novelty or the improvements that are done in AI, but link it to chip design or system design that we can use on wearables. And that's why you need to combine hardware and software optimizations. I would argue that literally this has been two worlds completely apart. So you keep seeing the people that do AI and create even larger models, and they do maybe some tuning. You want to map it on board, which is pruning, quantization, these type of well-known techniques. But these are completely coupled to what we do at the hardware, on the hardware side. When we do on the hardware side, we typically want to have elements that are voltage scaling, approximate computing. These are things that actually seems very different or very far away from what you do in software. But in reality, I would like to advocate in the lecture today that this is really not true. Actually, they are very similar. You find ways to propagate dependencies between the hardware and the software. That's what I think the concept of IoT and wearables, HAI wearables for healthcare can really play a big role. Now, last but not least, that I want to have as a first starting point or ingredients for our new design of HAI architectures is the fact that we're not doing general purpose computing. That's another thing that is very often neglected. Very often in the literature, you see is that you collect data, you send it to the cloud, and then this data in the cloud is processed. But this is not how you actually do wearables today. So in general, the way that is done, first, you have all the data in the cloud in the past, but this is not the way that you want to do it. It's a lot of energy sent or spent in sending all this data to the cloud. So the machine learning models should not run only on the cloud. They have a high latency and a lot of problems of data privacy and data traffic. But you want to move them really where you capture the data. Why? Because if you want to have something that happens, you can react much easier in the edge. So you have a wearable device, you have an arrhythmia, you have something that can degrade in a heart attack. You want to tell the person at that moment, not after 15 minutes that you send it to the cloud. So that's why you can actually solve many of the problems of the cloud large scale models by having these models running on the edge. You have to solve the problems of latency, privacy, and traffic. Now you create additional problems on the edge because if you're moving the computational complexity from the cloud to the edge, you are creating a large problem on these devices, and now they have to be pretty large on the memory to be able to save all the data you need to process, including these AI models. You have a problem of battery because if you spend a lot of energy, you will run out of battery. And if nobody wants to recharge your wearables every few hours, you need to make sure that they last at least for a full day of operation. And then you have finally a problem of computation because you need to really put much more computing capability on the edge, on the sensors. Now, I argue this is a very challenging problem, but you have also some good things there, which is it's not a wearable design, so you can know very well what it's going to do. So the system in reality, that's similar to embedded systems, is very much specific to the application target. So what you have in general, it's not that you need to have a big GPU and running all the time and so on because you know what is coming. You know perfectly what is coming. So you know that, for example, you will do for a cardiovascular pathology, you will have a part of the system that will be on, which is what you see here, acquiring data every now and then. In particular, the heart is a very slow signal. So it's not at all like running multimedia or audio or video. So it's extremely slow in the order of few hundreds of hertz. Most of the time it will be off. You only need to acquire signals every now and then. Then you will start processing when you acquire enough data to get a certain analysis. And only at the end, if you see that something is wrong with the analysis, then you will activate the communication and then you send the signal to the doctor. So you see, it's pretty well known. It's a flow that is very well clear. You have it very well understood since the beginning, so you can minimize system energy by only switching on and off things whenever you need it. So we can play with that a lot. And finally, last but not least, so overall, I hope I have shown you that in this case, one single architecture does not fit because you want to customize it for the specific application and the person. So you go to the literature, what you will find for HAI in general, you can find that there are many accelerators. In the past, they used to be done by general purpose, assuming that you have no knowledge about the application. So you will have multi-core, CPUs, and so on. Then this evolved to have more specifically systems that do data parallelization or exploitation, which is DSPs, vector machines, or GPUs, but still they have very high energy consumption. So what you will have on the other extreme, for some specific types of analysis, which are, for example, some types of filters that are very useful in machine learning for wearables, or typical CNN, you will have ASICs, application-specific instructions computers, which actually are very good from the energy efficiency perspective, but they are very application-specific. And we have a problem with that is that these models on wearables keep changing. So every 6 months, you have a new one. So you cannot really adapt so fast and create chips for all this. Now, my point here is that I think we can go a little bit in the domain of domain-specific accelerations for wearables. So you can combine a number of accelerators that exist in that area. We can do processing in memory. You can do systolic arrays. You can do CG arrays, so coarse-grained reconfigurable arrays, and you can even use somehow in some elements some kind of low-power FPGAs. Now, the point is that this is the recent focus that we have seen in AI wearables, and I'm going to cover it a little bit on the literature, and I will advocate that none of them is the winner. So you cannot really make a system if you use one of them. You need to combine multiple, and I'm going to show you examples that I hope I convince you why we need to have a lot of research on that area, and that's why, for example, the Asina Center is a very important center because you can actually have multiple people talking about the different systems. So let me go a little bit on this framework so that people understand what I'm talking about. So this idea of doing accelerators, for example, systolic arrays is something that came from the cloud, and then it started being mapped on low power systems. So you have here some of the famous examples you can have, which is the Halo system. That was actually, it's a systolic array for mythic analog matrix processing. That was actually done, was very famous. It was actually moving some of the high performance computing work to the considering energy efficiency. So you can reach 3 tera operations per watt, which was much better than general purpose systolic arrays. You can have Mythic, which is a similar one. And you can have finally HTPU, which is basically an array of 2D processors working in a SIMD fashion, very general. So in the end, they have even less energy efficiency than the other two. But has been deployed by Google, so that's why it became famous. But it's not, to be honest, as you see the best case here. Now, there's a second part that we are missing here. Still here, you're looking at the digital part. You can also think of, okay, well, you need to gather the biological signals, so why don't you combine digital and analog all together? Okay, and here there's a very interesting exercise that was done. You have some of the groups that actually like the group that were done in Navion, which is for a visual inertial odometry acceleration for robots, for drones in particular. You have some other exercises of chips where they combine the ADC front ends of wearable signals, like the BioWolf and the group of Luca Benini. And there what you do is that you co-design the front end with the digital part. So you try to optimize and to do it in a way that you can really reduce the amount of energy spent on the digital part by pre-filtering some of the energy on the analog. So these are interesting exercises, but I still argue that they are still focusing on one family of accelerators, okay? And if you do this exercise, I have been trying to map, and there were several studies that were done in the last few years, you see that they have improved, of course, the energy efficiency with respect to many core or GPUs, but all of them, if you take any of the three that we are looking around here, systolic arrays, spatial, or beams, processing in memory, you see that all of them, they kind of converge to the same domain on acceleration. You could argue why? Well, it's very simple. Basically means every family of accelerator is good for one part of the whole biosignal context. And in the end, they cannot optimize the whole system. So they only optimize one part of the whole application flow. And in the end, you optimize very well one, but then the other two you cannot. So in the end, the overall energy efficiency of the system is the same. So my point is that how can we do to go beyond this efficiency plateau that has been reached by all the accelerators? Well, why don't combine them? We should try to combine them and see if we can do the best of each of the two or each of the three worlds. Of course, there's a complexity here that you need to find ways to really map efficiently different pieces of the application in different accelerators. And that goes to the part of co-design. So the idea is that you have typically the hardware and the software, as usual in our community. And when you do machine learning deployment, the ML deployment typically targets, okay, I do, in the literature, I do machine learning by using a specific hardware. Good. So you got a good improvement on the energy efficiency of the system, and the performance goes up. But it's a moment that you reach a level that you cannot go better. There's no way to go better. As I showed you, you reach a plateau. But then you go up in the abstraction level and you start analyzing the application, you see which are the missing blocks. You could do another approach by doing, at the moment, lightweight training for the elements that you haven't been able to map in your accelerators. And then this is what is called tiny ML optimization. And you do retraining, knowing which is the hardware that you already have, and you repeat the process. And if you go in that direction, you can start iterating, and every time you do an accelerator, you remove the parts that are inefficient and you map as much as you can in them, and you go again. And if you do that, you will use in the end maybe 3-4 types of accelerators, that I'm going to try to show you next. And this will actually give you a much better overall energy efficiency because you will go up in the curve, like doing like a little stair every time that you actually retrain. Okay? So the idea here, the key idea here is, and this is actually the way that our brains and human beings have evolved, is that you iteratively learn and you improve a little bit. Okay? Not find one solution for all. This doesn't work. And the idea here is that you can do efficient use of resources, and as I said, importantly, using the knowledge that you have of the application, and you architecturally improve little by little to try to use accelerators for different parts of the application. Okay? So now, before I go there, I wanted to actually make a little catch on the part of analog versus digital, because I think there's a lot of importance on the analog part and the application domain that we need to exploit in this idea of accelerators.
Oh, one question regarding the
Yes.
MW means a middleware, right?
Say it again?
So MW here.
Is the middleware, yes. Middleware.
So when we are deploying the software, basically the algorithm on the hardware. So we need to go through the middleware, which means to change the behavior of the algorithm or the software a little bit, right?
Yes.
So we saw a lot of paper just assume that won't change. It basically just directly deploy, whatever the matrix or something to the hardware without considering scheduling, all kind of stuff. They say this, everything will be aesthetic, who can optimize. So, but actually, it may not be the case.
Absolutely not. It's not the case. The only thing that there's one extra thing that is beneficial here from the middleware, from the scheduling in particular that you mentioned, is that in the biomedical application domains, luckily the flow that is required by the doctors is pretty static.
That's right.
So you can exploit this knowledge on the middleware part to make sure that it's done. But I fully agree with you. You need to really, as you see, deal with efficient collaborative use of resources, assuming that there's a change between the software and the hardware.
I see. Okay.
But you will see that in a second. I will try to explain that.
Sure.
Okay. But so before going there, which is actually a good point, I wanted to actually emphasize a bit more the part of what people have been doing on this analog versus digital comparison, because I think there's plenty of things. Since we are using machine learning for everything these days, you can actually exploit very well how we have learned or how our human bodies have emerged or evolved over years. So, for example, if you think about the brain, you think about how the brain works, it's a huge embedding computing system, right? So it's you think about the size, it's around the size, total size, you can think of 4 to 100 micrometer neurons, which is relatively large. Actually, you can do smaller, but actually it's three-dimensional. So you have a huge amount of computing power, which is in the order 1.5 decimeter square cubic operations that you can do. So you can have in total approximately 80 billion neurons, which is a huge amount. You say, how can you actually make sure you don't run out of battery doing the day yourselves? And the point is that indeed, it's huge connectivity-wise. It's also really humongous. So you have 100 trillion synapses connecting these neurons, but you only consume 20 watts on average. Or I would argue, you can recalculate, there was a number that came from Jan Rabai in Berkeley, but I think it's pretty close to that, more than 10,000 teraflops, and you only consume 20 watts. And you can say, how is it possible? We don't reach these levels today with our computing. Well, you have a video here which shows you a little bit idea. You get a lot of data coming in, but most of the brain is off, right? So only very few pieces are triggered every now and then when you receive enough information. And that's what actually really comes into play. So we need to redesign completely the way we think about computing. The computing is, in this case, in particular for biosignals, we are very fast. We can do actually very fast the computing. Our electronics can do computing even faster than us. So the idea is that what you have to do here is to change this concept and change from being always on to being on whenever is needed. What do I mean with that? You think about in the time domain and you have the voltage of the signal coming in and you see the, like I said, the scope of the picture there, you see that there is a stimuli coming in and you have a threshold when you say, okay, this is meaningful to do something. So most of the time, the data that arrives to the neurons means I'm not giving anything useful to process, so I'm not doing anything. And then after a while, you see a huge excitation, and then you see these huge bubbles in red that operate. So this basically means that the neurons operate in a very different way than what we think about computing today. For me, it has 4 different features, which is what goes into the part of the HAI, or should go into the HAI. One is neurons are idle most of the time. And for me, being idle means no power consumed. And there's a huge overhead in the brain to do power management. So our brain, you think it's a lot of computing, but a significant part of our brain is about not doing nothing. So it's about being able to switch off the energy and not being consuming so much. Second part is that neurons, as I show you, only react to events. So you can get a lot of data, but most of the data is not useful for doing anything. It's not something that requires attention. Third but not least is you need to integrate the storage and processing. So many of the operations do not separate memory and processing. You don't have a processor and a memory and you send the data back and forth. The neurons integrate both things together. And finally, neurons are reconfigurable. You learn when you are young, you do things well in a different way. When you're older, you become much better in other things. You can be today very good at PowerPoint, not so much as good at maths, but this evolves over time, right? So our brains are really dynamically reconfigurable. And that should be actually something that we put in our HAI. So my idea is, why don't we design, and I'm putting this idea of the biologically inspired to something really more specific. We want to design something that is event-driven, architectures that are adaptive, with domain-specific properties, and accelerators that can be reconfigured. So these are the 4 main properties that we want to have. How does it work? Okay, so let me just go for it. This goes first to the part that actually Jinan says, okay, but you have the software, when you map it, is very different. So indeed, and there are changes that happen there. Now, the lucky element that we have is that we can play with a lot of things for scheduling. Not everything has to happen at the same time. And in general, when you have biosignals, you have the data coming in, but the data that comes in a very modular structure phase. So you get the signals. When you acquire the signal, you remove a lot of things that is noise that you don't really want to see. So this is a filtering phase. Only when you have finished the filter, then you start doing the part of enhancement of the signal. So you want to acquire elements that are important in the signal. The rest you kind of discard. Then you do feature extraction to see which elements are needed for you to do something, to understand the events that are important. And finally, you do inference or classification to understand what happened. And this creates, first, a very modular structure that helps you to do a scheduling when the things should be on and off. And second, a lot of these phases in biological systems that should be the same in our computing is approximate. I mean, I don't know precisely when my arrhythmia happened, but if I have an arrhythmia for a few seconds, I'm sure I will see it. Okay, so that's what we have to actually play with. And that creates a lot of opportunities for doing speed-aware computation, co-design, and even creating accelerators. Now, how do we put all these things together? So let's first start with the part of acquisition. So if I think of acquisition, well, that's something that is very interesting. So you want to train machine learning algorithms today, what do? You pass all the data to the machine learning. But much of the data that you pass to the machine learning is not needed. In reality, the machine learning wants to look at few elements that are important to characterize what event happened. The rest you don't need it. Okay, so if we think about the brain, that's exactly what happen in the brain. So you will do here is imagine that you have your electrocardiogram, your ECG signals, and what you will care about, and your doctor will care about the P, the QRS, and the T, which are the fiducial points are called, which are the main ones that trigger any pathology or event that is wrong in your body. Okay, so and in between you have these intervals that are between the P, QRS, T events that are not really so meaningful. So instead of using typical sampling that you do today, regular sampling, which is what you typically do, you do a time frequency analysis. What you see is that these events are very different. Some parts on the P, the QRS, and the T require high frequency sampling. Some others require low frequency sampling. And not everything is the same. So doing the acquisition at a regular frequency that we typically do today in medical devices is not optimal. From the analysis perspective, if I want to learn what's going on, I don't need this thing. Indeed, when you take a step back and you look at what software like Philips, healthcare systems, and so on, they do, they get the signal. The first thing they do, they decompose the signal and they make completely an uniform sampling that is different. So they decompose the signal. For example, here you're decomposing the signal in wavelet coefficients. And you see that from all the coefficients that you have, for example, a 2-second entry signal, which is 512 coefficients at 4 milliseconds sampling frequency at 250 hertz, well, you see that most of the values that you acquire are 0 or close to 0. So from the 512 samples that you acquire, you roughly need around 30, 40. The others are completely useless. Now, interestingly, today, what you do is you get the biomedical devices that are certified to have very high acquisition signals. They get the 512. They pass it to the digital part. The digital part says, oh, I don't need all this. And throws away, like from the 512, 450. So you spend all the energy acquiring all this data, transforming it from the analog to the digital domain to throw it to the garbage. And then, of course, this one, you pass it to a machine learning will say, I don't need it either because I don't need this thing to learn. So what you have to do is to change that. And the idea was to create, and we did it with Texas Instruments, some kind of level crossing strategy where you only detect events. You don't sample at a uniform frequency, you sample when you know that something is supposed to happen. So you dynamically tune the frequency that you sample to adapt to the signal that you're acquiring. So it's very much, I agree, signal specific, but gives you pretty interesting results. So you get the values. Up to a certain threshold, then you get the signal. If you don't get the value of the threshold, you don't care. You keep waiting. You get the second threshold, then you adapt the signal. And you keep doing that on the P, the QRS, and the T signals. And what you get in the end is a signal acquisition that looks like this. So you have your ECG signal. But in the end, what you see at the bottom is the sampling frequency. You see that the sampling frequency changes quite a bit. And you focus on the parts that are important for you. And the other parts that are in between the events, you don't do anything because you don't care about the signal.
Now, you can implement this on the hardware.
Yes. You implement it on the hardware and you can dynamically tune the hardware based on what you need. And even per person, we have the signal that is actually done by one of the startups of the lab called Smart Cardia that does precisely this. And this gives you a very important energy savings. Yes.
So you do the comparison in analog.
Yes.
Okay. But the one thing is like, what if you're running this in a noisy environment? So for example, like I know, I moved from the States to Europe and I have different frequency from this, and all of a sudden, because I'm picking up the power grid in this room, all of a sudden, like I will trigger and completely mess up this threshold.
So it's important. So what you're saying, if you have noise levels, because this one is the ECG. So when you're actually having an ECG wearable and you're monitoring ECG, I mean, the environmental signals, they're not really affecting you. What you will have is noise coming from your own body. You tell me that you flew from the US.
No, one thing is like, if you have a wearable, if you're using this type of approach, and let's say like I know you move from Switzerland here, you calibrated your system so that you remove 50 hertz, you come here at 60 hertz, even like from the power in the building. All of a sudden you have this structured structure the interference that is not just like a white noise that might mess up with the thresholds.
Yes, so what you can do in that case, we have done in few cases, what you do is you can oversample. So actually you don't even need the sampling frequency that is there. I will show you in a second. You can oversample even at that range. So you have a certain robustness on the sampling frequency that you can play with. And even if there is noise, you have a template of what you expect to see, and you can match the noise that you have with the template, and that will help you remove the noise.
Okay, but I do apologize for.
No, it's
but
perfect.
Then, like, I know, if this would be then very user specific.
Yes, it is. And that's what I'm saying. So very often to run these systems correctly, and that's actually how it's going, is really personalized wearable design. So every person should have his own wearable, which is not definitely done today because it's very expensive, but if you can manage, this is the best way to get to the point.
Okay.
Let me show you an example. So for example, imagine that I want to detect something that is happening on your heart. So I'm actually putting here a low ventricular activity, which is actually what you see there. It's not something bad, so you will not die with that. But I think because it's very obvious for you to see. That's why I chose this pathology on the heart. You see, it's very obvious. You look at the signal, you all see that somewhere is there. It was a very low ventricular charge. So basically, you will have a problem. Actually, you will feel tired. If it happens very often, this is that you will feel like very tired during the day. Okay. So what you will do instead of something that you will do normally at 360 hertz, going with your wearable in Europe, US, Switzerland, or whatever, what you will do, you create a model of that person. You know how the system is going to be for you because you measure at the hospital once, and you say, okay, this is the template of the person. You can even reduce the sampling frequency, like I said, because you do this selective sampling, and you can start doing the sampling instead of 360, 1 order of magnitude less. You can do a 37 hertz. In the string case, because you know how the reconstruction is, you can even go lower. You can go at the order of 5 to 6 hertz. And this is good enough to know because you know what you are expecting to see in that person, the type of pathology. Okay, so and you go there, you keep it at a very low frequency, and then when something doesn't match the original signature that you have for that particular person when it's healthy, you switch the frequency and you increase, and you make it robust to the noise. And in that case, what you have at the noise, very detailed reconstruction, is still 1 order of magnitude less than what you have absolute, what you have to the normal sampling frequency in medicals, and you can capture very well what happens, and then you go back to your normal sampling frequency. Normal means very low. So what in the end you get is a very reliable still system, but with a sampling frequency that you move between 360 hertz to something that is less than 20. So you are saving almost like 15 times the energy that you will have to have in normal sampling frequency. Now, the argument here, because people very always say, oh yes, but is it medically certified? Doctors will not care how you sample the signal. What they will care is how much is your accuracy and sensitivity at the end, on specificity. So they will look at the F1 score, and they will say that the original high quality signal at 360 hertz gives you 99.73 accuracy. Sorry, 99.79 versus the new one that we have, which is low sampling frequency, is 99.73. In the end, yes, you degrade a little bit, but this is still within the noise because actually the required sensitivity and specificity you need for a medical device like this for arrhythmia detection is in the order of 97, 98%. And then you will get it automatically certified for FDA or CE approval. So you are still okay. And that's what the doctor will care. They don't care about your final sampling frequency. They care about, can you detect what's going on with the patient? And the answer is yes. Okay, now, you have removed the amount of signals because in the end, that's another benefit for you. Instead of saving all this energy on your memory system, you are sampling a lot less, you are saving a lot less data, and still you're going to pass this data through the machine learning to really learn because that's the important features that actually are captured. So you make even more robust your machine learning because it's not getting confused with data that maybe is not needed anymore. So you only pass what you need. Now, if you want to do something else, the second step is that, and I wanted to enter there before we go to the architecture, which should be, if I manage to get you there, the easiest part is, okay, so you are sampling very well, you get the ECG because you put a patch here to sample, but what happens if I want to monitor your brain? How would you monitor your brain? You need to acquire the signal. So the typical way today that you will need to have sparse events, fine, that we already know how to do that because we know you adapt the frequency, that's okay. You want to make sure that it's real-time and personalized, okay? We can make the whole system go to the hospital to do a first pre-characterization to tune the personalized model. But there's a third angle that all the companies will say, and you need to make sure that you guarantee user experience. Otherwise, the person will not use it. What's the issue here? The patch was good because you can hide it under your clothes. But if you want to monitor your brain, how would you do it? Like this. Will any of you wear these very nice EEG caps? I can promise you they are wonderful for keeping your hair straight and stuff like that. But I honestly, I'm not sure, maybe with the future, in the future with Elon Musk, we'll be all happy to be like this, but I don't think it's the case. If you see someone like this on the street, you know that the person is sick, must be seriously sick. Otherwise, you will not go like this on the street. So that's the point. So even if you say, okay, I'm reducing the sampling and so on, you still have to deal with another issue in wearables, which is you need to make sure that the user experience is correct. In the sense, you need to make sure that you don't interfere with the life of the person. So it means that even if you want to, you will not be able to monitor these 24 channels or 36 channels that are typically on the EEG caps, but you need to live with a lot less and maybe monitoring different parts which are not optimal. That's the second part we need to deal with in wearables. Now, the nice angle here is that you have, even though you have to do with high accuracy with sensor in suboptimal positions, you can play with one thing that is our body is one thing. So in the end, if something happens on your brain, yes, it will affect your brain, but also it will affect your cardiovascular system, and it will also potentially affect some of your muscles and stuff like that. So if you do indirect monitoring on multiple biosignals, you can compensate for the suboptimal measurement on not the of a single signal. Okay, so my point is instead of monitoring with 36 channels or 24 channels of the brain, I can monitor with few channels and I complement the signal with information coming from other signals that are easier to wear. And that's the idea. So here, what we have done, and that's the concept, is you have like a network of wearables. What is the idea of the network of wearables? You have, instead of having the cap, for example, for epilepsy, what we are doing now, we are wearing a couple of glasses. So a pair of glasses where you monitor few points, because if I put you few electrodes in the glasses, you will not mind, because anyway, you're wearing the glasses. And then I put you also a chest sensor, and I put you a watch. And with these three sensors, I can collect the data between the three. I can run a first level of machine learning in each of them. If each of them, they detect a pathology, then I can put all of them together, and they start working together in a federated learning fashion to try to figure out if something is wrong. And if they detect that something is wrong, but they don't know what's going on, they can even share the information with the doctor for anything that happens there. Okay? So now the thing here is that, well, but hold on, if you're going to send the data to the cloud, a person that is having epilepsy maybe is not so happy to do that. So no, but that's the idea here, because when using AI and machine learning, if we exploit the way that you make the models for AI and machine learning, you can actually do it without sharing the data. And that's the beauty of this concept of federated learning that we have actually working with Jiran for a while. So as well, what you do is that instead of using typically what you do traditionally in machine learning, that you have your data on the sensors, you send the data to a centralized learning place or repository, and you train the model there. You can train the model locally on the devices, if the devices are powerful enough, and then you only share the coefficients of the model with a centralized learning place. And this way you preserve the data because everybody keeps the data local. So you are solving the problem of data privacy and sharing. So the idea here is that you can actually make this system, but then your HAI wearables now need to be very powerful because they also need to do not only inference, but they also need to do training on the edge. Okay, so this is anything. So now that we understood all the constraints, how do you do that? Okay, so this is the design flow that we are developing and that we have developed that includes a number of steps between hardware and software. So the idea here, you have your machine learning model that is a CNN or a complex one. We make an embedded ensemble of CNNs or machine learning, which is what you see there as a first step. Basically, we decompose the model in pieces that can be going to each of the wearables. So in each of the wearables will include one specific whole multiparametric, but only one piece in each wearable. Okay. When you do that, you are defining the constraint of your hardware. So which type of processing you need to run for each of these submodels. And then you can design your accelerators accordingly. And then the second part is you have your quantization. At the end, you start reducing the models. And then you can then optimize and see which elements should go to the memory directly. So you can actually do computing directly on the memory. So in the end, what you have is a system that has multiple families of accelerators that will be iteratively tuned when you're optimizing your software. And every time you change the software, you change the hardware. Okay? So how does it look like in practice? So what you have in this case, I'm going to just show you a little bit. So imagine that I'm doing my optimization of the CNNs. So I have my big model. And what you do in literature in the machine learning community is to take this and replicate. But you don't want to replicate. You want to just simply, you don't want to replicate because you will consume much more memory. So what you want to do is you want to take your initial model, split it and compress it. And when you do that, automatically, what you're going to consume is a lot less memory than if you just simply copy the same model multiple times. In other words, what you're reducing is that you're taking the original model that has a lot of sparsity and redundancy. You first remove the redundancy, and then you assign it to different sensors, okay? And if you do that, you are reducing the computation for each of the HAI sensors, and you're also reducing the amount of memory because every model will be different, okay? The nice thing of doing that is that when you look at the final optimization network that you have, for example, in the case of epilepsy, which is I was referring, the original model, we have a complex CNN structure where you have layers, parameters of the convolutional layers that have 8 and 16 bits, and the fully connected layers which had 16 or 18 bits. You start applying this quantization and splitting, and you get to values which are 4, 5, or 3 bits. These are really what you need, not what the software guide tells you. What you really need for the application you need to process is 4, 5, and 3 bits. Now, the point of having these 4, 5, and 3 bits is that if I tell you, run it in a processor, you will tell me, yes, wonderful. So my processor is 4 bits, 8 bits, 16 bits, or 32 bits. I cannot run it on 3 bits because I'm going to waste the energy for this. So how do I do? So the point is, indeed, I cannot do processors for that. I cannot do a systolic array or a CG array for this, but I can make in-memory computing very well because I can run it directly on the memory and I don't need to do that. So in the end, when you do this whole process, you can remove everything that you need. And in the end, what you need to run is very few elements that are needed for the accelerators, okay? Because the others, you don't care about processing on the accelerators, you process it on the memory. So what does it mean? It means you need to create an heterogeneous architecture that includes at least 2 families. One, for the processing in memory, and second, include accelerators for custom number of bits that can be reconfigurable for different type of kernels. So we tried to talk to companies. We went to ARM, we went to a few others. I'm not going to enter into the names. And we thought, look, can we have access to your computing architecture to change it? And they told us, absolutely not. You can buy our chips. That's what we have. And that's what you can use. So I decided a few years back to do similar to what Luca Benini, a colleague at ATS, did for high performance. And look, let me do the same thing for wearables. And we created a framework which is called HIP, with coming from extensible, heterogeneous, energy-efficient platform. And the X is what allows you to add accelerators. And we created a set of basic blocks based on a small RISC-V CPU. And the RISC-V CPU includes a memory block and a connector, so interfaces for all the typical peripherals that you have for biomedical. So ECG, EEG, and so on. And then this framework is open source. You can download it. It's called HIP. You have it available there. It has a repository and everything like that. We use it for projects with companies and so on, and you can create your own accelerators without paying any royalties. And that actually triggered a very interesting exercise when we put this thing and we said, look, you can build your own accelerator and you plug it in, and we give you interfaces for all the sensors. What turns out is that now the HIP community includes 35 research institutions, 15 companies, and more than 60 accelerators that actually are available in the repository. And anybody can go there and choose. Okay? So just to show you an example, so what we did for epilepsy is called special chip that we call it Hippocrates. I'm not sure you have heard about Hippocrates. Hippocrates was an ancient Greek physician that used to play what at that moment was considered the initial evolution of classical medicine, or father of the current medicine, because he was very much eager to adaptive situations. So he didn't like the idea of using the same treatment for everybody. So he was very innovative and proposing different things for anybody. So with that, we created our chip Hippocrates that includes exactly that. So it includes a small processor, which is the one that synchronizes the signal acquisition and the tuning of the ADC front-end to be able to be adaptive, as we showed you before. Then you have a bunch of accelerators and memory banks. So these memory banks allow you to dynamically switch on and off whenever you need them. And one of them includes in-memory computing. And then we have a number of accelerators, which includes very small computing and CGRA, which is for coarse grained configurable arrays. And we have the whole system. An important part there, which is just to make it clear, is the DMA to share data between the front end and the analog part and the power management unit. And I will go back. The power management unit is important for you to realize this is what we took from the brain. In the brain, I told you a very important part of the area of the brain, it's about power management. So here you're going to see that in our chip, which is this one that you see here, Hippocrates, we designed it in a way that is very small. As you can see, it's a tiny one. It can still run in a very old, we took very simple technology for the time being, 65 nanometer, but actually you look at the power consumption, it's in the order of microwatts, which is pretty interesting because it's very competitive with respect to other much more performing and newer technology chips, and you will see that. The nice thing of this is that this accelerator, you open it, it looks like this. So you have your little CPU in the center, you have a part which is always on. So you have this always on part, which is, it looks like it's a lot of overhead. Actually, this is the power management. So this is a part that allows you to dynamically switch on and off every single element that you have in the system. Actually, for one tiny chip like that, we have 12 power domains. So you can switch on and off anything that you want. And the idea is to switch anything with the middleware, going back to what Jiran said, that you know where you are, and you switch off everything that you don't need to consume very little power. And then you have the two accelerators. You have the coarse grained configurable array, I will show in a second before we conclude. And then you have one of the memory banks, which includes B-line computing, which is a number of logic that is here to be able to treat the data in this bank without sending it to the CPU or to the CGRA. Everything is done locally on the memory, okay? So how do they look like, these two accelerators? And before I conclude, so look, the first one is the CGRA. The CGRA, for those that have not seen it, it's a very simple concept, which is kind of, you can think of it as a generalization of SIMD, single instruction multiple data scheme, where you have, in this case, 16 cells that can be configured to do different operations, and you can pass the data up to 4 cells at the same time to do 4-level SIMD. And what you get is a little overhead with respect to a systolic array. What do I mean with that? You have your flow, which is much more efficient, so much more flexible. You have your synchronizer and controller that decides which cells are active at any moment in time. You have your 16 reconfigurable cells, which are the data path. Basically, is where you process the data. And then you have the DMA, which is in charge of feeding the data in and out from the memory, so that the data is always loaded. You don't put the processor to do that. There's a specialized DMA for that. And then you have 2 additional overhead, which are the 2 layers that are the overhead that give you the flexibility or the configurability, which is the context and kernel memory, which is the store, the CGRA configurations. So at any moment in time, you can run normal CNNs, different levels of the CNN, and you can dynamically change what you put in these cells, okay? Now you go, well, yes, but you have an overhead, which is these 2 guys here. Well, when you do the calculation, the overhead is around 15%. Everything that you see here is the overhead, all these guys together with respect to a systolic array, it only consumes like 15% of the area. Now, energy-wise, which is the most important part, is very efficient. So actually, the whole system, and these are different kernels that you can actually download. We have a repository for that, which is called MBioBench, that we have now released as well, which shows you typical kernels for biomedical signal processing that you can try to use and see how efficient you are. You will see that for all of them, the CGRA is always much better than running in a normal processor. So it shows that even with a little overhead, you are much better than the rest, okay? Yes?
I do apologize for that. Just to fully understand the application at the end that you use this for is just for what part of the accuracy? Just detection of the attack or
is a whole detection of when it's going to happen, the attack. So you have to be continuously filtering the signal. Like I showed you at the beginning, you filter the signal, you extract the features from the ECG. So you do basically the full process that is here. So you have the 4 phases that you have here at the beginning that I showed you. So you have this one. So you will get your signal from the EEG. You will filter the signal with the noise that you have.
You're looking from this or from the glasses?
From the electrodes here.
Here.
Yeah. So from the 4 electrodes, you will have the signal. You remove the noise because actually there is a lot of noise when you move and so on. There's a lot of noise. You filter that. the filtering is done in the CGRA. The enhancement of the signal is done in the in-memory computing part. So you don't need, because the enhancement is very simple process. So you don't need to send it to the processor, you do it in memory directly. The feature extraction is done in the CGRA as well. And the inference is done in the CGRA. So the enhancement in this case, for example, which is a very simple process, you don't want to send it to the CGRA, it's a lot of energy. You just simply do it directly in the memory. But you use here the two accelerators that I'm showing in the system. Okay?
Well, one follow-up question, if you don't mind.
Yes, go ahead.
So since you're optimizing for power, in your application that you're considering, have you noticed that, for example, if you are comfortable with spending extra power, extra resources, that you would improve, for example, robustness to noise, or like kind of variability within patients, or pretty much robustness to noise is done with filtering, and there is no way to deal with robustness patient variability?
No, very good point. So there are many different things in epilepsy in particular, but also in other ones you can do. There are several types of approaches for filtering, enhancement, and feature extraction in particular. The three elements there are very different. Even the inference, which is different types of machine learning, there are plenty of different options. Now, you can play with that. Now, most of the elements most of the data for many of the patients, they don't require very extensive filtering. Now, you can customize your flow for every single person if you want to, and you will run different kernels for every single person. Now, you can go a little bit up or down, but the reality is that very often for epilepsy, what bothers more the patients is the false positives.
Yeah.
Which basically means that you get a device that is telling you that you're going to have an epilepsy, you're going to have an epistatic, and you have nothing. So basically people get like 20, 30 alerts per hour that are not going to be realistic. And that's why you want to go improving on that part, not on the accuracy of the detection, for example. So it depends on the target application you have, but I agree. So I fully confirm that you can have different kernels for the different phases.
But is there, and I do apologize, I don't
No.
want to go in, but like when you're using like in some sense of, as you say, approximate computing for different stages, is there any way to make more systematic decision on, hey, I care more about, for example, this type of features, and that's where this part needs to be more accurate versus that one?
Yes.
Or is it at this point trial and error?
No, you don't have to do trial and error. So we have, I don't think I have it here. We have an F1 score curve that we have created for every application. Let me see if I have it. And that one, it allows you to move on the different phases of the curve, and depending on what you really need or you don't need, then you can actually tune the system accordingly. But we can discuss offline. I will show you then. Based on the different kernels, you create basically an F1 score curve, and basically you can move in the curve according to what you require. And that basically that gives you the thing. I'm sorry, I don't have in the slides here on the backup, but I'm happy to show it to you later. So depends really what the doctors want. Very often in epilepsy, for example, like I said, they care about the false positives. That's one of the main issues. Okay. Now, once you do that, like I said, one of the nice aspects that you can have, and is if you want to play with that, you have an open source version that we have done of the CGA. It's also available in HIP. If you want to play with that, in case you don't know, you can just go there and download it, and you can play with the parameters. Now, we have done the same exercise, and the nice thing here is that you can see that there is a significant amount of energy, like 70% energy saving with respect to general purpose CGRAs that exist. So the idea here is that you can definitely run very well. Now, not to run very much away of the time, an interesting angle is that you can also have the second one, which is the memory computing part. So what you do in this case, and that's very interesting, just to comment to people, in general, you think of in memory computing and you take the memory and you modify it. But this is not really what you very often do. Why? Because if you go to TSMC or UMC and any of the global foundry companies and production companies for memory cells, and you tell them you're going to modify the memory cells, they will be looking at you like, you don't do that, because we have spent a lot of months trying to optimize the memory cells for high density and so on. If you modify this, it's not going to really work. So we have to change completely the concept. So we don't do modifications of the memory arrays. We actually play with the periphery building blocks. And that's what you have. You have the lower part, is what we call bit-line computing. So what you do, you don't touch at all the memory bank. So you don't have at all modified the memory bank. This is the standard memory cells. But at the bottom, you added a little bit of logic, like the one I'm showing here, few transistors that actually allow you to activate more than one memory line. And this allows you to actually do simple operations like AND, NOR, you can do inversions, you can do shifts, you can do ripple carry other, and so on. But the interesting thing is that if you think about it, these are the type of operations that machine learning requires. So many of the machine learning algorithms, we can run them directly on the memory, which is a nice thing. Now, you would argue, yes, but actually you are adding an extra overhead here because you're having a huge amount of area here. Yeah, it's true. We actually kind of spend for the overall area that we need around 30% of the area, 32% in a 20 nanometer TSMC design that we made recently to study this recently in 2023. You need 1/3 of the area for the bitline logic. Now, interestingly enough, yes, you use area, but I go back to my point. Area very often is not an issue. What matters is the energy. The energy is very competitive because in the end, with respect to a normal read operation, all this area are most of the time off. So you don't spend the energy on that. So indeed, for one read, a normal read in a memory, if you do an in-memory operation, you're pretty much spending the same energy as reading and significantly less than a write. Okay? So in the end, you spend a little bit of area, but you're not getting a lot of heat on the memory, energy consumption, and you get an improvement in performance, which is significant. Okay? So overall, the final design of Hippocrates, and you can compare this with two state-of-the-art designs, Apollo 3 Blue, which is a commercial version, it can do very well, very simple heartbeat classifier, but it cannot do well training, for example, or AI and complex machine learning. You can take a more sophisticated design like App9 that was done in the group of Luca, and in the end built by a company. And then the idea here you have is that it can be more efficient than you in some parts, but in the end, on the other part, it's actually worse. So overall, with Hippocrates, which is a low-cost design done in a much worse technology than any of these two guys. So Apollo 3 Blue, for example, is running on 40 nanometer TSMC, and Gap9 is 22 nanometer. We are talking about 65. So we are huge orders of magnitude difference on price and technology-wise, and we are still competitive. Okay, so that's the idea, that if you do the same exercise with new technology, you can get better. Now, the nice thing is that I encourage you all to try. It's an open source platform. You can use it, happy if you use it, for whatever you use it, I don't mind. That's the point. Whereas if you take any of the designs from Gap9 or Apollo, they will be very unhappy you use it for something that's not what they're looking for. And here, I don't care. It's actually the other way. So now, last but not least, as to conclude what I have, of course, we learned. So this was on 2023. So now in Q4 2024, we have two more tape outs coming up. One is called Hypatia. I'm not sure if you knew Hippocrates, but Hypatia was the disciple of Hippocrates. So Hypatia was actually one of the most advanced pupils he had, was a lady that was extremely smart. And she said, look, it's not only about doing improvements on the way you diagnose, but also it's important on the tools that you use to diagnose. And that's what so we have done is a new chip, which includes not 2 accelerators, but includes 3 accelerators. So we have now the memory computing, the CD array, and then a systolic array, and an additional extended computing on the external part for DRAMs when you want to do training. And when you do that, you have actually a much better energy efficiency. That's what we claim. We are going to see that in January 2025 when we get the pin back, and you will see. And Hypnosis is another chip that we are doing with a company. It's an interesting exercise, which is about, has a special accelerator called Maxwell, which is for near memory computing, and it's about detecting stress on people. So we're going to see if we can detect stress. And that's actually part of the initiative that I explained to Jiran recently that we have been approved in Switzerland called Swiss Chips, which is the same as the CHIPS Act in the US. And we are actually leading that area with EPFL and CSEM, and we are happy to actually join forces with you guys to try some things on the Athena Center. Now, just to finally show you something that is the full system. So I told you I will replace my cap with my glasses. So these are my glasses. So the glasses include a sensors EEG 24-bit 3 channels. So I only have 4 points of measurements here around the part where the actual glasses fit on the person. So you don't have to have weird shapes and so on. We have accelerometer and diodes to filter the signal and the noise. We have several interfaces, Bluetooth to 0. Then we have an ARM Cortex M3, and then we replace it with our Hippocrates, and you see, I have 64 megabytes of memory. So you can do up to 7 days of EEG recording with a single battery recharge. And the battery of the whole system can run within 24 hours. So you can definitely charge it. We don't have the problem anymore of using it for a few hours. We have a second version because here I always had the same catch. People, yeah, but I don't wear glasses. I don't like to wear glasses. How do you monitor me if I don't wear glasses? We have a solution for you. So we have a second version, which is this one, which is called Epiphone, which is a bone conducting headset. So you like to play to listen to music or play sports. You put it, you will be able to listen to music through the condition of your skull next to your ears, and you still can monitor your EEG. Actually, even better than the glasses, because the glasses, the point that people typically tend to have, which is normal, hair here. So this creates a lot of noise, whereas I know very few people that have hair here. So here you will be able to monitor much better. So I encourage everybody to these days to use bone conducting headsets so I can monitor your brain very well. So that's the idea. And here's the system that you see, one of the examples of the test that they did with one of the students there, monitoring in comparison with a medically certified device, the BioPack. And you could see that the signal that we acquired, you see it on the left, which is much easier than in the video, is very, very similar quality. So you can get extremely high quality and you can detect everything without any problem. But now, so the main point that you want to argue is that, okay, this is done. Can you generalize? So this is the last system that we have done now. We moved for our network. We have not only the glasses, but we have a system called VersaSense, which is a multi-parametric board that you have your watch, your chest, your thing here. It's a little board that goes in connection with the glass and Epiphone. And you can use even normal watches if you want, but we give you otherwise a watch. And the whole thing is that it's able to detect 90% of the machine learning seizures with respect to a cup. So you don't need to wear a cap anymore, and you still get the same accuracy. It looks like this, a little bit the system. So it's a little box that you can divide and make it pieces. You can put it, like a mechano, you take the box, you demount it, and you put it wherever you want, and it will start measuring. So it will create a little network, and the network will start measuring, and it looks like this. So you have a board, which is our Hippocrates board. You have the main board for connecting other sensors from the state of the art. You have the EKG, which is for ECG and variations. You have the EDA, which also does the brain, and you have the hardboard that do the whole thing. You can use it. You see many configurations. For example, this one that you see on the upper part is the one that we use for epilepsy you're going to run. The second one is for doing cough detection, and this is the second one that we have, which is actually interesting for doing stress detection, and you wait only here. And the whole thing, like I said, all these guys can work with each other, which is what we implemented the further learning scheme. So the device with Hippocrates can train. So every now and then you send the data from the device to the central gadget, which is here the main board. You adapt it again and you bring it back, and you can run the whole system iteratively. And in the end, what we get from 90% with a single sensor, we get now 98% accuracy for epileptic seizures. So we have actually a new exercise with the University Hospital there in Lausanne, because the doctors are very excited about it. So we're creating a spin-off, which is going to start commercializing this board most likely next year. We are running right now a large-scale training set. I was mentioning to Jirena, it's a fortune what goes into this medical test, but it's actually worth it, I believe, if we can improve the health of human beings. So we are running a large-scale training and testing of around 3,000 patients. We are hopefully going to get to the point to do it. But bottom line is that you can get plenty of new ideas how to train these on-device training architectures. So I hope we can do that with the next, not 5 + 2, 7 years of Athena. So we have still many years to work on that. I hope so. So, but just to illustrate, so I hope I have shown you a little bit how this IoT era and HAI can work also for the context of wearables. So the point is that wearables are very interesting, but you don't want to go like this on the street. Nobody would like to go running out of battery and with a solar panel on the head to really power up the solar cells. So you need to reco-design, and I hope I have shown you how you do it methodologically, and you can run between the analog and the digital with accelerators. And I think the next challenge is to run even more the on-device learning, which is something new that appears there. With that, I conclude. Thank you very much for your attention, and I'm open for questions.
Yeah, we're a little bit over time. We'll still be able to have maybe 1 or 2 questions from the audience. So, any questions? No.
I have a few questions before we're a little bit longer, but
That's okay.
Helen.
I have one question.
inference, how do you coordinate the signals from different sensors? Is it also like on the devices or on the phone? Yeah.
Very good point. So there are two, the way to synchronize is that the sampling frequencies of the devices, remember, this comes from our original design. So this comes from here. So remember that before I created the division between these three guys, I had a supermodel. It was my complete neural network. So this was when I already know what is the sampling frequency of the devices. So I make sure the sampling frequency of these three devices are compatible. And then that allows me to then merge them when they come here. We have a central board, which is one of the three. In this case, very often, typically, is the smart cardiac patch that is the more powerful one of the three. And that's the one that makes the whole synchronization for the three to send it to the cloud.
So I have one follow-up question regarding this, because we actually developed a framework which can allow us to support the application of a foundational model,
Okay.
model, for this device. We try to minimize, the computing resources which we require on the edge device, so can still be able to support that. So we have our edge data center with the connections. We can offload everything to the data center. I think we should consider how we can expand what you already have, maybe open up the source to us, so we can deploy some foundation model rather than large language model partially on this device.
Absolutely. And then we can definitely, one of the nice things, like I said, of HEAP, and you can see this, that we can change it so that we can configure it very much dynamically and flexibly. So there's a plenty of elements that we can change here. The memory can be large.
Right.
We have added now the idea of having, like I show you, a secondary memory, which is the DRAM and an external flash. So we have actually the option to have part of the foundation models or the tuned models on the flash. And we have developed a scheme now to dynamically load pieces of the thing on the memory for training.
Yeah, so Jimmy, can you really consider we just deploy some adaptation layers on this device, but not the whole LAM, by assuming we have a sufficient bandwidth, to send the interface to the adaptation layer on this device. Yeah, and also, we had another example to show we actually, she does work, to just use a foundational model to process, those signals without really train them model. I think we can talk about it.
Okay.
So this is how it's going to be quite useful for us to demonstrate what we already have.
So for me, I have two areas here. Like I said, one is that it's really the part of learning, making the devices much smarter on the learning phase, and coordinating with the cloud is what I think is a very interesting area to work on.
Yeah.
And we are creating very strong accelerator like this historic array that you have, for example, in the.
Yeah, that's what I'm thinking, how to use the hardware you already implemented.
Exactly. So in the, you already have Hippocrates, which does quite a lot of things, but in the new one, in Hypatia, you have a systolic array and a lot of memory that you can do there. So we can do plenty of things there. Now this chip is not there yet, so we just actually have it ready to be sent to TSMC in 16 nanometer. We are going to actually do it now in November. But the previous one, we have it and we can already play. One interesting thing I didn't mention, and it's actually good that you said, we can already start working on this because the model of its HIP works on an FPGA. So we could already start, and we do it a lot with the companies, that they can already work on the mapping and so on, taking our full model, running on the FPGA, and then see how it actually works and so on. And we finally just replace the FPGA by the actual chip. But we have a full framework that you can run it on the FPGA. We even have a way to, do you have data that you want to use for the training? Or because we have even a virtual ADC that you can actually simulate as if the data is coming to your model at the speed or frequency that you require.
Yeah, we'll get some follow-up on this. I'm thinking how to use the hardware you already have. So
Yep.
okay, so
There's one question online.
Yes, please.
I can read it to you. You talked about more sparse sampling and presumably therefore model inference patterns. However, it sounded like you alluded to sparse conditional weight and activation usage. Are there any research directions in this area that make you optimistic for low power medical devices, or do you think that irregular memory access patterns incur such a performance cost that current directions are not currently viable?
So good point. So there are two things I didn't mention. So the idea of using a sparsity in wearable devices is already very well known. So in fact, we showed sometime back, I think almost 10 years ago, a design of compressed sensing based ECG sensor that works very well. So you can actually, definitely you can use sparsity in many different ways. Here I was showing or illustrating that in a very simple case where you can actually selectively choose what you bring in from the ECG, but you can do it in a general case in a normalized phase. Now I agree with you that the problem that you have there is that you have random kind of accesses to the memory. Now the problem there, and I would argue that, is that very often what you will do is that you will think, oh, I had the data in the memory, which is a very irregular access pattern, and I had to take it out from there and send it to the processor. But with Hippocrates, you don't have to do that, like I told you, because what you can do in this design, you simply process it in the memory. So the fact that you have a very irregular memory access pattern is not an issue as long as the data that you need to process is in the same memory bank. By the way, we could also extend it to multiple banks. I'm just saying in case we want to reuse the hardware that we already have. But this midline computing part, we can extend it to multiple memory banks, and you don't have a problem of sparsity or memory access pattern that is sparse, because anyway, you're not doing anything outside the memory, so this sparsity doesn't bother you.
Okay, that's a good applause for our speakers.
Thank you.
I think we have quite a few things we can follow up.
So thank you very much for the people online. See you.
Yeah.